Welcome to this explainer. Today, we're diving straight into the magic behind the everyday technology you use to tape out messages. Ever wondered exactly how your devices seem to literally read your mind, anticipating the exact word you're trying to spell after tapping just a letter or two? Well, today we're exploring the brilliant architecture making that possible, the Trie-data structure, also commonly known as a prefix tree. So let's really think about this. How does your phone know what you're typing before your thumbs even finish moving? A traditional database lookup simply can't keep up with that kind of speed. If an engineering problem involves words, prefixes, or autocomplete features, standard hashing is going to be way too slow for those rapid-fire prefix queries. And that means a specific data structure, a trie, is almost certainly your answer. Section 1, Anatomy of a Trie. To understand how autocomplete pulls off this magic trick in real time, you kind of have to picture a trie as this massive family tree of letters. It's a tree data structure where each node represents a single individual character. By linking these characters together branch by branch, it allows for blazing fast insert and search times. Specifically, we're talking about big O of M time, where M is simply the length of the word you're looking for. It makes searching for strings so much faster than sifting through a giant, unorganized database. Now, the real secret sauce here is the node structure itself. Every single dot, or node in this tree, is built on a base structure called a trinode. Inside that node, you got an array of children with exactly 26 slots. That's one for every lowercase letter in the English alphabet. And right alongside that array, there's a simple Boolean flag called isEnd. It's basically just a true or false signal to mark when a sequence of letters forms an officially completed word. Section 2, How Tries Actually Work. Okay, so we've got our individual nodes, but let's move to the mechanics and see how this builds into an actual working system. Inserting a word into this structure is beautifully logical. Step 1, you just walk down the characters of the word you want to insert. For each character, you check your 26-slot array to see if that letter's spot is empty or null. Step 2, if it is null, you create a new node for that letter and move down into it. You repeat this for every single letter. Finally, step 3, after all characters are placed, you just plant your flag at the end by setting that isEnd Boolean to true. And this brings us to a crucial difference when you're actually reading data back out from the tree. For a full, standard search to return true, you absolutely must find every character in the sequence, and that final node's isEnd flag has to be true. It has to be a complete word. But a prefix check, or startsWith logic, is a whole different ballgame. It demands that you find all the characters in sequence, sure, but it completely ignores the isEnd status. It honestly doesn't care if the word is technically finished, which is exactly how your phone guesses prefixes instantly. Section 3, Real-Life Example, Spell Checker. All right, let's take everything we just went over and explain it again, but this time using a real-life example to really lock it in. Imagine you're the one building a spell checker for a massively popular messaging app. You need to store millions of words. How do you efficiently store and search for two highly similar words like cat and car without completely wasting processing time and server space? Well, if you were using a standard database, you'd save cat and car as two totally separate, distinct entries. But a trie handles this so elegantly. Both words start with the exact same C and A prefix path, so they literally share those nodes. The first node is C, the child node is A. From that shared A node, the tree just branches off. It points down to a T node, where we set isEnd to true for cat. And from that very same A node, it also points to an R node, where isEnd is set to true for car. Instead of storing them as entirely separate entities, our spell checker shares the C and A, which saves us an enormous amount of lookup time. Section 4, the big trade-off. Now, as with everything in computer science, there's no free lunch. While this sharing structure is lightning fast, it comes with a pretty huge engineering catch. We already established we get that blazing fast big O of M time complexity for inserts and searches. But the trade-off? Heavy, heavy space complexity. Because every single node holds an array of 26 elements, even if 25 of those slots are completely empty, the memory footprint can get absolutely massive. In fact, a trie can easily eat up megabytes of memory just to store a basic English dictionary. So to combat this giant memory footprint out in the real world, developers have a really clever workaround. They'll often just swap out that fixed 26-slot array inside the node for a hash map. A hash map only takes up space for the letters that actually exist as children of that specific node. This trims down the memory overhead significantly, all while keeping that lightning-fast tree structure perfectly intact. Section 5, Build it to learn it. Look, understanding the theory of nodes and arrays is great, but putting it into practice is where it clicks permanently. Seriously, if you take the time to build a trie from scratch just once, you're going to instantly recognize when to use it to solve massive engineering problems. Once you code those insert and search methods, the logic applies perfectly to building autocomplete features, spell checkers, complex word search games, and really any system where you need to find all words with a given prefix. Which brings us to a final thought for you. As you go about your digital life today, typing in search bars, sending emails, looking up contacts, I challenge you to look at your favorite applications and ask yourself, where else is this brilliant, invisible prefix tree hiding? The trie is absolutely one of the most elegant data structures in computer science, and now you know exactly how it works. Thanks for joining me for this explainer, and keep exploring the hidden structures that shape our digital world.